Good morning. My name is Ruri Hiromi from White Project. Today, we will talk about our effort in deploying IPv6 called v6fix. We have two topics. I will introduce v6fix. That is an effort to solve problems in IPv6 deployment focused on IPv4 and IPv6 dual stack environment. Technical analysis of specific problems found in real world. In the next, Kenjiro will talk about tools and measurement. Let me start with the current status of IPv6 deployment status. Currently, the majority of equipment and software are already IPv6 ready, such as major routers and operating systems and applications. But we have still many applications and appliances work only with IPv4. In addition, IPv6 has been getting in various business fields such as sensor networks, building automations, and other kind of business new field. However, most people lack knowledge and experiences on IPv6. When non-experts encounter a problem, they are often clueless. We think that is the problem. Here is an example. Hotel internet systems have an instruction for their guests. They said for the troubleshooting, if you have IPv6 enabled, please disable IPv6. This picture is the real brochure of the hotel. The cause of the problem was a combination of two factors, we suppose. One is the DNS redirection system always returns specific A resource record for any kind of CAT queries. And client stub resolver accepts the A for CAT and can't go anywhere. I will talk details later. And it found that faulty behaviors are only 1% and often combinatorial, but it could be fatal to acceptance of IPv6. In addition to the hotel internet case, faulty behaviors come from such as slow fallback to IPv4 when encountering IPv6 errors, misbehaving DNS resolvers, filtering out of ICMPv6 packet by firewalls, DNS misconfigurations, poorly configured tunnels, and lack of peering or IPv6 capable path. That we think known problems are just the tip of an iceberg. We need to act now, or they would bring a negative impact to the IPv6 deployment. We set up a research group called v6fix to technically identify, analyze, solve real-world problems in IPv6 deployment. Our enemy, we think, after trials and errors, disabling IPv6 fixed my problem. After several problem analysis, we realized the importance of cooperation among researchers, implementers, and operators. Because overlooked problems are often found at boundaries of specification, implementation, and operation. There is a v6fix covers topics: harmful effects of the on-link assumption, misbehaving DNS servers and resolvers, slow fallback to IPv4 after failure of TCP connection attempt, misconfigured firewalls, comparative analysis of the quality of the IPv6 Internet. Here I show you two examples. The case one is the DNS loop at hotel. As I talked before, it is a real story. We went to the same room and investigated the problem. The problems are as follows. DNS is intercepted and redirected to the sign-up page. IPv6 enabled users can't go beyond the first page. Hotel has an instruction for disabling IPv6. Caused by a combination of erroneous DNS redirection system and stub resolvers, it turns out that caused the problem. The redirection system always returns the a specific A resource record for the sign-up page when receiving non-A queries. Client stub resolver queries CLAT A first for any addresses and always receives the same A and blindly accepts it. In this case, it could proceed the whole process, but users encountered a significant delay in responding name resolution. This is also a real story. And Japanese ISP upgrades their DNS cache server to bind 9 and received complaints about slowdown. The user said, it is not comfortable in web browsing through your network. After their investigation, they built bind 9 without IPv6. Then the problem fixed and reported it at Japanese Network Operators Group. This caused by order bind 9 without IPv6 connectivity. The server without IPv6 connectivity always tries to talk over IPv6 and ends up when falling back to IPv4 after timeouts. Fixed in bind, the current version of the bind 9 has been already fixed the problem. There might be three factors. The problems appear only with specific combinatorial conditions. The implementers and operators did not notice the problems until someone reported the problem. Even for the professionals, it wasn't easy to track down the problems.
Okay, I'm Kenjiro Cho. I'm going to cover measurement results from this project. So Ruri talked about the specific problems. And here we are trying to get a big picture of the current deployment status. So our goal is to understand the macro level status of the IPv6 deployment And we are using two different technologies. The first one is the wide area measurement of the behaviors of the second level and third level DNS servers. And the second measurement is comparative path analysis with IPv4 and IPv6 dual stack. So here's the results from DNS server measurements. So basically we're trying to figure out the number of DNS servers that cannot handle quad queries. This is within .jp domains. And the table basically shows percentage of the faulty servers. So about 0.13%, just 0.13% of the servers currently cannot handle quad queries. And the details are listed in the bottom table. And most of the problem come from lame delegation. It's not listed here. But there are other reasons. The one is DNS servers ignore quad query. And the second one is DNS servers returns rcode3, its NX domain. So if they cannot, they don't have quad records, they have to return no error with empty answer, but they return NX domain. And there are other types of servers that return other kind of errors. So the percentage is small, but still these servers are out there. And when people are using IPv6, users sometimes encounter these problems. And here, I'm going to talk the second measurement. This is the dual stack path analysis. So we are trying to develop measurement techniques specifically designed for dual stack measurement. So the idea is to take measurement for both IPv4 and IPv6 at the same time and compare v6 results with v4 results and extract problems that exist only in IPv6. So we are trying to separate the problem of IPv6 network from IPv4 network because currently most of the IPv6 networks are deployed over IPv4 using tunnels. So we're using methodologies that consist of 3 steps. So the first one is dual stack node discovery. We are trying to create a huge list by monitoring DNS quad replies. And using these lists, we're using dual stack ping. Basically, this is a pin and normal pin and pin 6 to the target list. And we select a few representative nodes per site, in this case, /48, by RTT ratios. And in the third step, we are running the traceroute and traceroute 6 to the selected nodes. And we visualize IPv6 and IPv6 path MTUs to obtain macro level path or v6 tunnel situations. And also we visualize v4 and v6 paths to neighboring sites for comparative analysis. So here is an example. This is a distribution of IPv4 and IPv6 RTTs. IPv4 RTT is plotted on the x-axis, and the v6 RTT is plotted on the y-axis. And the left picture is, left graph is from NICE-net results, and the right graph is taken from ISC. So if the IPv6 RTT is similar to IPv4, nodes plotted around the unity line, but if the individual nodes are plotted far above the unity line, it means basically deep issues. And if there is a cluster of the unity line, there are some problems in backbone. So in this left graph, there are lots of nodes plotted above the unity line. So there must be some problem in the backbone. So this is hard to see, but we visualize the trace route results using GraphBits utility. And this is basically to visualize path and MTUs. So edges are colored by MTU. Blue lines are basically MTU less than 1500. So it means tunnels. And nodes are colored by RIRs. And this is measurement is from NISANET to RN sites. So, so many sites from NISANET to RN sites are going through Japan. So this is a typical problem of lack of tunnels. And this is what we saw in the left graph. So lots of sites, when you're using IPv6, path is basically going through Japan. And this is from ISC to RN sites. So path looks much better, but there are lots of blue edges. That means there are lots of tunnels still out there. So Abilene case in the NISANET results a well-known problem. So Abilene has been trying to encourage IPv6 adoption, and there are no AUPs, or they provide tunnel services for IPv6. But Abilene ended up with horrible IPv6 paths, mostly with tunnels. Because many ISPs are pairing with Abilene, and they just don't want to move to paid IPv6 connectivity. So I heard currently Abilene is thinking about suspending its relaxed AUP for IPv6 to encourage ISPs to move to commercial IPv6 connectivity. So our tool is used to illustrate such issues, and we are hoping to help convince operators to move to better IPv6 environment. So this one is an example of dual stack trace route visualization. This is from White to Abilene. We plot neighboring sites and their paths, and each target is plotted. In this figure, 10 targets are plotted, and we plot B4 paths and B6 paths in the same graph. So in this graph, they have similar RTTs or hops for IPv4 and IPv6, and basically it's a native dual stack path from White to Abilene. So this is an example of commercial path. So currently, commercial paths, basically they are using completely different routing for B4 and B6. So these nodes have similar RTT but different path. This is very common in the current B6 deployment. And this one is the example of B6 has much larger RTT than IPv4. They are basically roundabout tunnels. So B6 takes much longer to reach the target. So to conclude, there are only few misbehaving nodes deployed in the IPv6 network, but often they are problems are combinatorial, and this problem could be fatal to acceptance of IPv6. So we're trying to list specific problems we encounter in the real world, and also we are trying to get a big picture and try to promote adoption of IPv6. And the important thing we realize is to share information among different groups, and especially we need a cooperation among researchers, implementers, and operators. So we believe we should act now, and otherwise, this problem could be very problematic to IPv6 deployment. So here we list our collaborators and people who help measurements. So information is available from here. And also our tools are available. It's basically Perl script and or other tools are written in C. So if you can share, for example, traceroute result, please try the tool and send result to us. Okay, thank you.
Are there any questions for either of our speakers here this morning? Please come up to the mic. No? If not, thank you both very much. Appreciate it.